Introduce kinetic molecular theory. Before we introduce the gas laws, Mr. Newbar and I are going to have these today. So I'm going to start by going through the left-hand side of the worksheet, or the note-taking sheet, and then he'll do the gas laws on the right-hand side. So in order to talk about the gas laws, we want to talk about ideal gases. In order to talk about ideal gases, we want to talk about the kinetic molecular theory. That's where we're going to start. KMT, kinetic molecular theory. It is the theory that addresses the behavior of ideal gases, which ironically, do not exist. There's really no such thing as an ideal gas. Ideal gas would be the perfect case gas where everything is simple and sweet. That's not really the case. So in order to pretend that we have ideal gases, we are going to need to make some assumptions. And there's not a lot of them. There looks like there's 5 of them. They're listed there for you. We'll just kind of qualify or explain them briefly. The first assumption is that ideal gases are made of tiny particles that are far apart. That's not really much of an assumption because they really are far apart, relatively speaking. In solids, we've got molecules or atoms that are pretty much locked right together. When we heat them up, give them some energy, they eventually melt. When they melt, as a result of gaining more energy, those molecules or atoms end up being able to separate, and they can move around relative to one another, but they're still cheek to cheek. They're still right next to one another. And then once we give them some more energy, eventually they are able to separate. That's when the water starts to boil and you see the steam coming off, going into the gas phase. Then we've got molecules that are far apart. So that is the first assumption, is that our gas molecules are going to be extremely far apart. They're going to collide. They're going to bang into each other. Air molecules are colliding all the time. They are going to collide with perfectly elastic collisions. And we've got a couple of different types of collisions to show you. Elastic collisions, elastic like rubber, like bouncy. Are the ideal case. The opposite of elastic collisions would be inelastic collisions. So I've got a couple of cards here that would represent our molecules or our atoms. Inelastic collisions are collisions where the two objects start initially as separate, they collide and stick together. Now instead of 2 atoms or 2 molecules moving independently, we've got one bigger molecule stuck together, moving as a larger unit. So that would be inelastic. Partially elastic would be a collision where they start out separately, they collide, and they still travel separately after the collision, but they're going to lose some energy. Now they're not losing a lot of energy here, just the energy that is taken to compress the spring. That spring is going to compress, there'll be some friction and a little bit of heat generated, so they'll lose energy in the form of heat. A perfectly elastic collision would be more modeled like this, where they travel independently, they collide, and they separate. Now these two guys aren't even touching when they collide because they're being repelled by magnets, so they're not losing any significant amount of energy in this collision. So that would be at least a good model for a perfectly elastic collision. Another example would be balls. We got happy and sad balls. Happy balls do what balls are supposed to do. They bounce. Sad balls, not so much. So this would be like an inelastic collision. This would be an elastic collision. Elastic, inelastic. Elastic. Oh, how'd I do that? Bouncy, bouncy. All of a sudden they're bouncing. That's crazy. Okay? That's good talk. So, In elastic collisions, we lose no energy. No energy loss. So we're going to talk about energy down here in step number 5. Particles are going to travel in straight line paths. For how long? Until they run into something. And when they do collide, they're going to collide perfectly elastically. So they're going to hit the walls of their container, or they're going to bang into other gas molecules, but they're going to collide, and they're going to travel in straight line paths until they collide, and after they collide, they'll travel in straight line paths again until they collide again. They do not attract or repel one another. So in the ideal case, they can go right by one another. In reality, this is our ideal case. What really happens is that they are going to have a little interaction and be repelled from one another a little bit. Well, we're just going to pretend that they're not, because that's still a pretty good approximation. And then finally, kinetic energy, that's the energy of motion. Abbreviated with a KE, the equation for that is 1/2 mv squared, where m is the mass of the particle, and v is the velocity of the particle. And velocity, if you don't know, is the scalar half of speed. So velocity is basically speed, but it also has a direction associated with it. So you drive down the road, 55 miles per hour, that's your speed. If you're driving down 55 miles per hour to the east, that would be your velocity, 55 miles per hour. East is a velocity, 55 miles per hour is just a speed. So as temperature goes up, the kinetic energy is going to go up. And again, that relates back to phase changes. That's why our solids, as the temperature goes up, they gain more and more energy. They move around a little bit more. Eventually they separate and turn into liquids. So they've got more energy. They move around a little faster. If they continue to gain energy in the form of temperature, thermal energy, they're going to start to move faster and faster and eventually be able to break apart and separate. Okay? Let's talk about properties of gases. Expansion, just like it sounds, expansion is getting bigger. Gases are always going to expand to fill their container. You know that if you take 20 milliliters of water from a small beaker and you pour it into a big beaker, it's still going to be 20 milliliters. If you've got a container that has 20 milliliters of gas and you place it into a 1 liter container, seal it up, those molecules are going to move farther and farther apart until they occupy that full liter. You open up that liter jar in a room like this, that 1 liter of gas is now going to occupy the entire classroom. So as a result, they have no definite shape. Or volume. The volume of the gas is the volume of the container. Fluidity. Fluids have the ability to flow. primarily due to their lack of attractive forces. So because they're not attracted to one another, they're able to just glide right past one another. Typically, fluids are liquids and gases that you're already familiar with, but solids can also behave as fluids. An example of a solid that behaves as a fluid would be like sand. Fine powders, you could pour them from one container to the next. Let's change colors. Low density. We know that density, I think we know, that density is the ratio of the mass per volume. When we put gases into a larger container, their mass isn't going to change. They still have the same number of particles, but their volume is going to increase, so they become even less dense in larger containers because they've got huge amounts of space between each molecule. That also is why they are compressible. They've got the compressibility characteristic. So they can be squished back together. If we can put them into a bigger box and have them spread out, we can also squish them back together. That does not work well with solids. It does not work well with liquids. Liquids and solids are not technically incompressible, but they have very, very minimal compressibility in comparison to gases. And last on our list here, diffusion and effusion. Similar, not the same. Effusion is the ability to pass through small openings. Simple example of that would be your helium balloons. You ever got helium balloons at a party or carnival or whatever, especially if they are in like your normal rubber type balloon that you can buy at the store and just blow up yourself. Helium is very small particles, very small particle that is able to slowly effuse, pass through the lining of the balloon. They use mylar balloons for higher quality helium balloons. Those are those that look like foil, real shiny silver ones. Those have smaller openings, though helium does not pass through those as easily. You also know that with regular balloons, if you blow them up just with air, oxygen, nitrogen, carbon dioxide, those are much larger molecules. Those balloons don't deflate nearly as quickly because those molecules don't pass through the tiny little openings in the vinyl or the rubber of the balloon. Diffusion is the ability to mix with other gases. So it happens almost daily when I'm teaching in my other classroom, but somebody takes out their little hand lotion and they're putting lotion on their hands, and within a few seconds I'm smelling cookies because of the vanilla scented lotion that they're using. Other examples, of course, you're familiar with relate to bodily functions where somebody in the nearby vicinity may have just released a little of their own gas, and within a few minutes Everybody's going, you smell that? And a person outside says, no, I don't smell. Oh yeah, no, I got it. So that's the diffusion of gases. And our last topic here before we pass it off to Mr. Neubauer is pressure. Pressure is measured with a barometer. It is defined, abbreviated with a capital P, defined as the force per unit area. Asked my last class where you would be most likely to break a toe, and the young man's hand went up and he said, on your foot. Okay, that's great. So the most, as reported by emergency rooms, the most common place that people break their toe is on an elevator.
That makes no sense, actually.
Does it? How come?
Because it goes down and in, and then you're paying attention, and you're going to slip off or something, and your toe gets cut in it.
Caught in the elevator door?
Yeah.
That's one way you could do it.
People gets crowded.
Yeah.
Yeah, that's what happens, is it's from getting stepped on. And it's not from getting stepped on by Chuck Taylor. Chuck Taylors don't break toes.
Oh, yeah.
They break ankles.
They break ankles.
People do up.
So the way people break their toes on an elevator is they're waiting on the elevator, doors open, a couple of business ladies step in, people step back, and then the ladies are standing in the front of the elevator as the doors close. When somebody else comes in, they step back on someone else's toe. So they don't weigh that much, so the force they're applying isn't all that large, but the fact that it's applied over a very small area, like the spike of their heel, easily breaks the toe, where if you can, I remember I used to let my mom run over my foot when she backed the car out of the driveway just because I wanted to see if I could do it, and I never got hurt because all the weight of the car was spread out over the entire area of the tire.
But don't do that.
Yeah, I wouldn't encourage you to do that. That's not like smart. That was back before I got smart. Okay, so here's a real simple and quick pressure demonstration for you. I'm going to apply a force, same amount of force each time, to try and squish this foam pad. It's pretty squishy. So a little bit of force will do it if it's applied over a small area. Cross-section area of my finger, not big. If we go a little bit bigger, I can still squish it, but it's not as easy. A little bit bigger yet, same force, bigger area, less pressure, less squishage. Bigger area, same force, not a whole lot going on there. Even more force, my finger's kind of turning red and white at the end. Very little pressure. This guy's a little bit bigger yet. And you'll see I can't generate any significant amount of pressure with this just because it's spread out over such a large area. So when you're walking across the thin ice, when you're silly enough to continue ice fishing long after you should be ice fishing, you want to make sure that you are spreading your weight. If you're concerned about breaking through the ice, you get down on all fours and crawl rather than walking on 2 feet. You spread your weight across 4 feet. If you're still nervous, you get down and you slide across your belly, or better yet, have a sled or something that you can kind of pull yourself along with. But if you need a sled, you're not very smart for being out there. Okay, so to define our pressure, we got force per unit area. In the SI system, force is measured in newtons. Area, distance is measured in meters, so area would be in meters squared. 1 Newton of force is a puny little force. It's about 1/4 of a pound. So you go to McDonald's, you get a quarter pounder, throw a little cheese on there to make it a little bit bigger. That's like a Newton burger. So 1 Newton of force spread out over 1 square meter, that'd be like taking this area and applying 1/4 pound of force to it. Not much. That's going to give you 1 pascal of pressure. That is puny. That is a little unit. It's just a little guy. So that's why we typically use kilopascals. Atmospheric pressure. Pressure exerted by our atmosphere on you is constantly pushing in on you, pushing down on the table, pushing everywhere. It's like being at the bottom of a pool. You can feel the water squishing your head and pressing on your chest. It's not quite that bad here because the air is less dense, provides less pressure, but atmospheric pressure is 1 ATM, or 1 atmosphere. That's an easy one to remember. 1 atmosphere is equivalent to 101.3 kilopascals. Kilopascals would be thousands of pascals. We told you this was a puny little unit, so atmospheric pressure is 101,000 pascals. That's the equivalent of 760 millimeters of mercury, which is another way to measure pressure, which is the same as 760 torr, another unit of pressure, which is the same as 14.7 psi, which are pounds per square inch. So as you're sitting here now, there is virtually 15 pounds of pressure being exerted on your body in every direction because you're at the bottom of this ocean of air. One quick calculation and we'll hand her off. Let's do a conversion between PSIs and kilopascals. We're going to go 7.5 PSI to kilopascals. This is no new shakes. This is the same stuff you've been doing all year long. The only thing that's different are the numbers and the units that we're going to be converting between. So we'll use a T-chart. It'll be a little guy. We want to go from kilopascals, or sorry, from PSI to kilopascals. So we write down what we're starting with, 7.5 PSI. Figure out how they're related. There's 14.7 PSI for every 101.3 kilopascals. Write that in the fraction form with our PSIs on the bottom because we want to get rid of them. 101.3 kilopascals on top. That's what we want. Cross out our units. Don't cross out the numbers. Plug and chug. 7.5 times 101.3 divided by 14.7 is 51.7 kilopascals. Done. Questions? Ladies and gentlemen, Mr. Neubauer. Are you looking for this guy?
That's fine right there. All right, so Mr. Blackford just got done talking about kinetic molecular theory and kind of how gases behave and why they behave that way. We're going to take this right into talking about gas laws. And we have 3 gas laws that we're going to be talking about today. And then we're going to combine them in one full equation at the end. So these gas laws that we're going to be talking about are essentially going to be describing the relationships between pressure, temperature, and volume of gases. And you guys have all experienced each of these gas laws in some form or another before in your life. So they should make some sense to us already. We have a little simulations of things that we're going to go through with to help hopefully understand them better. Then Friday we're going to do some demos with them. And next Monday we're going to be doing the lab where you guys are going to get to explore them yourselves. So today's kind of just our intro for all that stuff. The first thing that we need to talk about and understand is something called STP. Okay, not Stone Temple Pilots. Mr. Gussie likes them. Or the company up here. And what it actually stands for is standard temperature and pressure. So we can write that down here right away. So it's standard temp and pressure. And we have some set units for what standard temperature and pressure are, and that's 0 degrees Celsius, or what we are going to be using is 273 Kelvin. Okay, so all of these laws are going to be using Kelvin, not Celsius. And the equations actually don't work out the right way if we use Celsius instead of Kelvin. And standard pressure is just our base pressure, which is 1 atmosphere. Same thing as 760 millimeters mercury. Same thing as 101.3 kilopascals, 14.7 psi. Any of those things. Okay, they're all equivalent. Okay, so the only reason we need to know is that a lot of times we're going to hear standard temperature and pressure, and we need to know what those values are. Okay. Next, we're going to be talking about before we get into the gas laws, we need to talk about just the units that we can see for each of these things. So we're going to be talking a lot about pressure, a lot about temperature, a lot about volume. The units for pressure that we're going to use are the ones that we just talked about. So things like atmospheres, kilopascals, psi, any of those things. Okay, millimeters mercury. I know I didn't put it on there, but any of those are appropriate units for pressure. So this is just helping you recognize what you're being asked to do. For temperature, you're always going to be doing Kelvin. And I am going to circle this guy as well because it is really important that we understand that we need to be in Kelvin. Okay? So a lot of us are going to want to do Celsius a lot of the time. Okay, but you're going to be given values in Celsius, but you're going to have to convert them. So the conversion is just our degrees Celsius plus 273. We did. Last thing, volume. We should be comfortable with units for volume already. This could be something like liters, milliliters, centimeters cubed, millimeters cubed, those kind of units. So when you see any of those, you're thinking volume. When you see obviously Celsius or Kelvin, you're thinking temperature. And when you see atmospheres, kilopascals, psi, and that stuff, you're thinking about pressures. Okay, perfect. We're going to get into the laws then. First law that we're going to talk about is called Boyles Law. So each of these is named for a person who either worked with this, discovered this, whatever. Okay. So Boyles Law is a relationship between pressure and volume. And all of you can at least imagine or have experienced this before. So for our example here, we have two syringes. Now what we're assuming is that basically we're plugging the end of each syringe. So we have a closed environment. Does that make sense, everyone? So you all know what a syringe is. Okay. When we have an open syringe, there's a certain number of gas particles in here. Okay? Like you're trapping them inside of it. Now, our syringe is capped. Now, if you can imagine, what happens when I push down on that syringe? There's going to be a point when it still looks like there's space in there. We know there's air there, right? And it gets really, really hard to push it closed. Like you can't push it closed. Makes sense, right? Because what we've done is we've taken this same number of particles, we've compressed them down, and now we put them in a much smaller area. So if we're talking about this in terms of Boyles Law, so we're relating this between pressure and volume right now. When we have a high volume, so right here on this side, that's a high volume. I want to know what will the pressure be like here. So when we have high volume, we have more space for particles to occupy. So are those particles going to be hitting the sides of the container more or less than if we close the space down, relatively speaking? What do you think? When there's more space or less space, are they going to hit more? When there's less space, right? When there's less space. When there's lots of space, they're not going to be able to run into and hit each other as much. When they're hitting each other and they're hitting the container, that's what we are perceiving as pressure. Okay? So when we have a high volume, we're going to have a low pressure. Now, we take and we compress all those particles down into one little space like this, like our syringe here. Okay? We have all these particles in a small space. They're still moving at the same speed. It's still constant temperature. We have a much smaller volume here. So is there going to be more collisions happening now or less? There's going to be more, right? And we're going to perceive that as an increase in pressure. So our pressure is going to increase when our volume decreases. Okay, that's why when you start squeezing it down, if you were to have this in your hand, and we're going to do this one on Monday, you'll get a chance to do this, you can't squeeze this syringe completely shut, right? Because there's particles of gas in there, if it's plugged. Okay, so we would call this an inverse relationship, right? Now, I have a simulation for you that kind of shows this as well. So, right here. Okay, so right now what we've done is we're leaving the temperature constant. So this simulation, what's going to happen here is there's a pump here, okay? I'm going to pump some gas particles into the situation. I'm going to leave the temperature be constant, and what I'm going to do is I'm going to adjust the size of the container. Okay, so we should notice what's happening to the pressure here as we change the volume. And you're going to see what happens to the collisions of the molecules as we change that volume. So, pump a few particles in here. Let's go a little more than that. Right now it's going to raise it up to a certain pressure, right? And you can see there's a bunch of collisions between those gas molecules. Those gas molecules colliding with each other and the side of that container is creating the pressure on the inside of the container. Okay, now, if I'm going to decrease the size of the container, so decrease the volume, what am I doing to the pressure that the molecules are at? The pressure goes up. There's more collisions. So we feel that as a higher pressure. Now, if we are going to decrease the size of the volume here, or increase, I'm sorry, the size of the volume, what happens to the pressure? It's going to decrease, right? Because there's less collisions here. Okay, so it's a good visual for us to see that. And we're going to be able to see that a little bit more and experience that more on Friday and Monday in our labs. Okay, so we have an equation here to figure out exactly how much it goes up by or down by when they're affecting each other. So we have an equation that says P1, okay, times, V1. So this is our pressure initially and our volume initially, equals our final pressure, our P2, times, why do I keep running P twice? Times our final volume, our V2. Okay, so this is our before, and this would be our after. Okay, so our example on here says a gas occupies 12.3 liters at a pressure of 40 millimeters mercury. So our pressure here is 40 millimeters of mercury. Okay, that's our P1 at 12.3 liters. That is our V1. We want to know what the volume is when the pressure is increased to 60 millimeters of mercury. So our P2 is going to be 60. And we are solving for V2. So basically what's happening is we're squeezing these molecules closer together. So this would be like the first part of our syringe here. Okay, the second one is right here. We're increasing the pressure on the molecules. So we want to know what the smaller volume is at that point. Okay, so all we're going to do then, multiply 40 times 12.3. We have to divide both sides by 60. That's going to get rid of this. Okay, and get rid of our millimeters mercury. And we're going to be left with a value in liters for our volume. Okay, and so we would get 8.20 liters here. perfect. Next, Charles' Law. Charles' Law is going to talk about the relationship between temperature and volume. Now, most of you have experienced this relationship before. Okay, if you ever had, I don't know, basketball sitting in your garage. Okay, in the summer, you probably inflated it the whole way, perfect. You're playing outside in your driveway. Well, now it's going to be springtime. It's still a little cold out. It's like 40 out. Okay, so you go outside, you want to play. You go to enjoy your basketball. What happens? It's flat. Why? Did air escape your basketball? No. I mean, maybe a little bit did. Okay, let's be real here. The seals aren't exactly tight. But let's say a little bit went out. But we're saying that all the air is still inside. Okay, what's another reason that the basketball is flat? It's because we've decreased the temperature. Okay, so when temperature is high, our volume is going to be big. When temperature is low, our volume is going to be low. Okay, and we can look at that in terms. Let's just look at it in terms of the simulation here first. So let's take a look here. So now what we're going to do is we're going to set this pressure here to be constant. Okay. And you can see what happens to the size of the container. Now what I want to do here is I'm going to add heat like it's a nice summer day. Okay, so we're going to add some heat to the situation. So what should happen to the volume of the container? The temperature is going to start to rise. We should start to see the molecules vibrating faster and faster and faster, and it's going to increase the size or the volume that the container has. Right? Now, it gets cold outside. Okay, let's say this is pumped up right now. It's all the way up. Now it gets cold outside. We add, well, in this case we're adding some ice to the situation. But what's going to happen? Our basketball is going to shrink in size. The molecules are less active. So the ball gets flat. Does that make sense? Perfect. So, I mean, another example of this that you all know is a hot air balloon. Down here, our temperature will be low. It makes our volume low. We add some heat to the situation. So our molecules are bouncing on the side here, but they're not going very fast, okay? So they're hitting the side of this. Now, we've got some little speed marks here, and they're flying around inside, and they're moving faster because of the increased heat. It's increasing their kinetic energy. So our temperature increases, our volume also increases. We call this a direct relationship. Okay, and our equation here then is going to be V1 over T1 equals V2 over T2. Okay, so simple problem here. It says the gas occupies 900 milliliters at a temperature of 27 degrees Celsius. That's our V1 and T1. So our V1 is 900.0 milliliters. Sorry. We're going to divide that by our temperature. Our temperature cannot be in Celsius though. Our temperature needs to be in Kelvin. So we need to take 27 degrees and add 273 to it to get to Kelvin. That's going to be 300 Kelvin. Okay, that's going to equal our final volume, so that's our V2, divided by our final temp. Our final temperature here says 132. We need to add 273 to that. If we add 273 to that, we're going to get 405 Kelvin. Now, everybody, when you're going to solve one of these, it's as simple right now as cross multiplying and dividing. Okay? So all we're going to do is take 900 times 405, divided by 300, and that's going to tell us what our new volume would be. In this case, our new volume is 1,215 milliliters. Make sure you include your units on here. Okay? And it should make sense conceptually, like you're increasing the temperature, you're also increasing the volume here. Okay? Last one. Last one is called Gay-Lussac's law. Okay, this one's, the last relationship would be between pressure and temperature. Okay, so what we're assuming here is that our volume remains constant the entire time. Okay, so this would be like, I don't know, if we had some sort of pressurized gas chamber or something like that. Like there's a lot of things like that, right, where we have gases under pressure. And the volume is not able to change. So we're going to talk about what would happen between the pressure that the gas is under and the temperature that the gas is under. Okay, so let's just take a look one more time. So we're going to leave the volume constant on here, and we're going to see what happens when we change our temperature. So we'll just keep the same number of particles inside there, and it's not going to let me do that. Okay, so we want to have a constant volume here. So right now our pressure is at about 0.38 atmospheres. Now what's going to happen here is I'm going to add some heat to the gas molecules. When I add the heat to the gas molecules, they should start moving faster. And when you see them moving faster, they're going to be colliding with each other and with the outside surface more, right? That makes sense. When they start to collide more with each other and the surface, the pressure that the system's under should go up. And the more heat you add, the faster they start to move, the more pressure you start to feel. Okay, until eventually it's a ton of pressure and boom, you blew the lid off. Okay? Point is, once again, direct relationship. As I increase temperature, what do you notice happens to pressure? An increase in pressure, right? It's all about those increases of collisions between the gas and the container that they're in. Okay? So, in our first box here, we'd say we had low temperature, and that's going to equal a low pressure. So we have these little gas molecules, they're bouncing around, they're hitting the side, we still feel a pressure, but it's just not that much. Okay, now on this side, our gases are moving at faster speeds, which is leading to an increase in temp and pressure. Okay, sorry, the temperature increase leads to the increase in the faster speeds. Anyways, we have an increase in temperature and we have an increase in pressure here. Okay, so it's basically the same relationship that we had between volume and temperature. Okay, it's a direct relationship. So here we're going to have P1 over T1 equals P2 over T2. Okay, so for this one it says a gas has a pressure of 0.370 atmospheres at 50 degrees Celsius. What's the pressure at standard temperature? So my P1 is equal to 0.370 atmospheres. I'm going to divide that by the temperature, which in this case is 50 degrees Celsius. I need to convert that into Kelvin. 50 plus 273 is 323. Now, I want to know what the pressure is at standard temperature. To get to standard temperature, we would just need to know that that is 273. Okay? Once again, to solve this problem, all we need to do is cross multiply, so 0.370 times 273, and divide that by 323. And that would tell us what our new pressure is. If we're decreasing temperature here, we should be recognizing that our pressure should be less. Okay? So that can help you get the right answer as well. When you go through here, just check your work. You should get 0.313 atmospheres. Okay, now, this is all saying, like, in a perfect world, we're keeping one thing constant all the time, right? But things aren't always constant, even in our basketball example. Like, obviously, when it gets colder outside, not only are we decreasing the volume of the basketball, but a big reason that we're decreasing the volume is because we're decreasing pressure as well, right? So all three things are really in play in many situations. So we have a law that's really combining all three of our gas laws into one. This is called a combined gas law. And it goes through and it includes each of those three relationships. And so for our combined gas law, it's literally just a combination of two. We have P1 times V1, which, if you remember, is Boyles Law, divided by T1 equals P2 times V2 divided by T2. That'd be our final and our combined law there. So we have one last example problem here. The example problem says, what is the volume of gas at 2 atmospheres and 200 Kelvin if its original volume was 300 liters at 0.25 atmospheres and 400 Kelvin? So it's saying our original volume is 300 and our original pressure is 0.250 atmospheres. So we're going to start out with 0.250 atmospheres. That is our P1. Our V1 is the 300 liters it originally occupies. It's already in Kelvin for us, so we can just write out 400 Kelvin. Okay, next. We want to know what the volume of gas is, though, if we change the pressure to 2 atmospheres and we lower the temperature to 200 Kelvin. Okay, so here we write our P2 is 2.0. We want to know what our V2 is, and we know the final temperature is 200 Kelvin. Okay, so if you look up here for just a minute, easy way to solve these problems. You're going to multiply, cross multiply, divide, divide. Okay? So it's the same thing as just like we could go through and just rewrite it and solve it, but it's cross multiply, divide, divide. So you get the final answer here. Okay? So you take 0.250 times 300 times 200, essentially divided by 800 to get your final volume here. And your final volume in this case will be 18.75 liters. Okay, Mr. Gussie is going to be handing out your homework right now. For your homework, a couple things coming up, guys, so I still need your attention here. For your homework, on gases 2 on your assignment sheet. If you take that out right now, your assignment sheet says that gases 2, it has 2 due dates. One says next Wednesday, one says next Thursday. Cross out the one that says Thursday, it's due on Wednesday. Cross out the Thursday. Due on Thursday. Also, on Friday, I will not be here. If you're in my mods 1 and 2 or 3 and 4, you will be in my room. If you are in Blackford or Gussie's after, well, any of your classes actually, any of their classes are meeting in this room on Friday. Well, any of mine either too. Anybody's classes are coming in here. Yeah, anybody's classes, not my 1, 2, or 3, 4. So are you good with that, everybody? If you're in 1, 2, or 3, 4 for me only, you're in my room. Everybody else is coming in here. On Friday. Good time to everybody.